Swayam Prabha. Digital India. Educated India.
Thank you very much for the introduction. Yes, colleagues. Right, I will make up for the time. So I'm using Mac. I've always been an honest believer in Mac OS and not Windows. And once in a while, it does disappoint me. But anyway, we've managed to get the file. Good morning, everyone, and welcome to this lecture. I'm just going to touch on a few issues. You know, whenever one has to talk about energy and water optimization, you seldom know where to start because the problem is really big. But I've tried very hard to narrow it down to just three issues that we've been tackling very recently with colleagues all over the world, including some of the colleagues here at IIT Madras. And that is touching on the textile industries, the shale gas exploration, and lastly, looking at just the unit commitment problem, which is very specific to my country, South Africa, at the moment. Those of you who might know anything about South Africa will be shocked to know that we have what is called load shedding, meaning that there are instances where we don't have electricity, maybe for a few hours, and that is because of the unit commitment problem. So I'll try to be swift. You'll have to help me here because this doesn't seem to work. So just migrate for me to the next slide. I'll start off with acknowledging a number of colleagues who played a role in this, whose work comes up in this presentation in one way or another. I won't read them out, but these colleagues are all over the world, as I did mention, here and in the US in the May. So if you can continue, and some of my students, of course. I'll just start off with the background and the motivation for the study, and then I'll get straight into the techniques that we've applied. And of course, with the understanding that not all of us here are really at the heart of mathematical modeling. Okay, so let's continue then to the next slide. So if you look at this was presented, by the way, and I'll try very hard not to belabor some of these points because they've been raised by some of the colleagues. The last 2 days have been really on these topics, water, energy, and other topics. So this was also raised to some extent by Professor Mushtaba. I'm not going to dwell on it, but the point that I wanted to raise with this particular diagram was where South Africa is at the moment. South Africa is one of the driest countries in the world. In fact, we are the 30th driest country in the world, which is really, really, really very, very severe, given that you have about 195 odd countries in the world. So to be ranked 30th is really serious. And for us, it's not economic scarcity, it is physical scarcity. I mean, we don't get more than 500 millimeters of rain per year, which is much lower than the global average. So that is where we are at the moment. Just continue. So water for us then becomes a very, very, very important resource to look into. And we have been looking at ways of solving water, but most of these ways are not systematic ways. So these are ad hoc ways of saving water, which every engineer, for example, or any experienced person would be able to do, but not really systematic method. It is really recently that we've been adopting systematic methods across the board, not just in chemical processes, but also in power generation facilities. I just felt that some of the quotations or quotes that we've had in the past are apt on times like this, that the water that we have is the water that is available. No more than a percentage that we can really directly use, no more than 3% that is available to us. The rest is captured somewhere in the ocean or the deserts that we cannot be accessed without interventions that go beyond nature. So we have to conserve whatever we have. So that statement there is really bad. I'm not really a firm believer in the war over water, but we've seen some of the remnants of that, the things that take us very close to that. There was a statement made by the former Secretary General of the United Nations that the next war would be on water. But we've seen some of these examples. The one that is very, very close to heart, I'm sure some of you are paying very close attention to this, is what is happening in Africa. At the heart of Africa, Ethiopia and Egypt. What you see there is the Grand Ethiopian Renaissance Dam. The construction started in 2012. This year, they had their first output of about 375 early in the year and another one later in the year. So they're sitting at about 750 megawatt of hydroelectric power at the moment. That was the whole idea. The design of that bridge is about 5.5 gigawatts. So they're still far away from the design capacity. But what it means really is that they would have to capture water from the source of the Nile River. So this is where Ethiopia is, and the dam is somewhere there, meaning that the stream that ends up somewhere in Egypt has been reduced. And that's a serious matter at the moment that has not been resolved. This took place during the Arab Spring, when everyone else was paying attention somewhere else. Ethiopia decided to go ahead and do this. So this was smart in a way. By the time the Arab Spring was over, the bridge was well advanced and they couldn't stop doing it. But when it's finished and it lives up to the capacity of 5.5, I don't know exactly what will happen downstream. But they were smart in the sense that the neighboring countries are very quiet about that at the moment. They'll be receiving electricity also from Ethiopia. So Sudan is very quiet about it, but Egypt has the problem. There are a number of examples for this. If you can continue, it would be nice if I could control this. Okay, maybe I can. Then there are a number of other examples that I cannot go through also because of time. I just felt that this one I'm going to bring up here. It's in the book that we published with Iqbal Mujtaba after we had a conference in South Africa at some point. But you can see this is affecting this particular state, Tamil Nadu and Katanaka. This is the Cauvery River. Tens of people, hundreds of people have died already there. Because of the dispute between the two states. We know about it. I wouldn't call it war, but it's something to be seriously concerned about. And the Rhine River in Europe is also another example. I can confirm that this is not working. Maybe just migrate for me. Let me forget about this one. Just migrate forward. Yeah, that's fine. So with that, then let me just go straight to the examples that I want to share with you. And I think I'll be able to be eloquent enough for the message to be as crystalline as possible. Sometimes it's difficult to do that. We have looked at these three industries in particular. And I'm sure that when I say shale gas, people would say, why is he talking about shale gas when we are now moving into renewable energy? But US is still very much into shale gas. Those of you who are working with colleagues in the US will tell you it's still very much for them a game changer, and they're not going to stop exploring it. So we are looking at ways of improving that. And then, of course, as I said, the last one is the UCP. So the textile industries in particular, let me just, not through words, but through examples, show why we are paying attention to this industry among other industries. We are currently, as humankind, and I think this is one thing that we must pay attention to. Next time you put on your clothing, from your shirt to your trousers, your pants, your suit, always remember this. We are the culprits of the energy or climate change in one way or another through this particular industry. This is one of the most destructive industries when it comes to climate, and we are paying very, very little attention to it. At the moment, there are about 100 billion items of clothing that we produce as humankind globally per annum. Most of those end up somewhere there. That's an incinerator next to you. There sometimes it goes to the landfill, and we know exactly what comes out of the incinerator. Between 1975 and 2018, the global per capita textile production increased from 6 to 13 kilograms per year. That's you and I, roughly. This is how much the amount of clothing we use since 1975. And that alone will contribute more than 5% greenhouse gas emissions in many forms, even before it gets to the grave or where you dispose of it or you put it on landfill. The production from extraction to transportation to processing involves a lot of greenhouse gas emissions. And globally, this industry alone consumes about 93 trillion liters of water per annum. Now, it's a serious industry that you must look into. And all of us are a part of that in one way or another. That is why we are paying attention to this. But if you go back into history as to where it exactly began, it was in 1989. Zara, by the way, I'm mentioning this. Normally, I try to avoid names of companies, but this is now well documented everywhere from reliable sources that the first company to go into what is called fast fashion, which was really a game changer for the fashion industry, was Zara in 1989, where it took only 15 days from concept, from where the idea was in there, the mind of the designer, to where the garment was out there for selling. 15 days. And before then, it would take about 6 months. And from then on, this is good for business, but it's very bad for the environment. And that's where the problem really began. So this was a news article about that, about the new lane that they had come up with to produce some garments. And the rest has never been, life has never been the same ever since. If you look at a simple life cycle or cradle to grave analysis of a simple gene, one pair of genes, from your cotton production, which we call extraction, to your fabric production, to your manufacturing, all the way to where you dispose. In most instances, we actually don't go this way. There's very, very recycling. Only 20% of our garments are recycled at the moment globally. 80% is not recycled. So that is very, very fictitious. You can go back here, and then this is the end of life. That is how it goes. So this particular industry has assumed what you would call a linear model, where you extract, you produce, you consume, and you simply dispose. That is what it is. And that is why then it's important to come up with techniques that will seek to inject that circular kind of thinking. That's what you're trying to do here. If you look at one pair, for example, so just to produce one pair from cradle to grave, you would emit about 11.5 kilograms of carbon dioxide. That is how much you emit if you drive 60 kilometers on a very good car. That looks like a good car, isn't it? You'd emit about 60 kilometers. About 11.5 kilograms of CO2 in a very good car. This is not your dilapidated vehicle. And then the amount of water just for a pair of jeans from cradle to grave is about 7,500 liters of water, which is how much we drink in 7 years. A human being would drink that amount of water in 7 years' time. That is just one pair of jeans. So surely it is an industry that we should have been looking at for quite some time now. And by its very nature, this industry happens to be a batch facility, the way it is. You know, some of the operations I had in some of the presentations we had that we're trying to move into continuous operations, particularly with the pharmaceutical industries. But some of the industries are inherently batch, and this is one of those. I don't think that this one will ever go continuous. So it will remain batch, which means that we still have to deal with the time dimension in this kind of a sector. So this is a typical example. For example, here you are processing about the 4 colors from white to dark. And it has tend to have different stages, as you can see here. It mimics what you'd find in an agrochemical facility. That's another facility that cannot be continuous for a number of reasons. So these have their own unique features that make them remain batch. So I'm giving an example here. So it is a batch facility, which means that we have to come up with ways of solving this. Now, batch plants, some of the colleagues here work in batch plants, are very difficult to analyze. We've been trying very hard for many years to come up with the practical ways of synthesizing these operations, of properly designing these operations and optimizing them. And we still are trying to do that because of the nature of the mathematical model that comes from there. So continue. So what we did recently, and that is a paper that we published about 2 years, a year or 2 ago. And they were using genetic algorithm in that paper with the colleagues here. And it's very, very clear that even if you look at the CPU times we're talking about are very, very huge. And what the message one is trying to send here is that if you look at the problem size, it tends to be exponential. Well, we say these problems are NP hard, where NP is the non-polynomial time. And that has been proven, by the way, that batch models tend to be NP hard, which means that an incremental change in dimension leads to significant change in CPU time. And that is what you see here. So you see that if you just solve, for example, the scheduling model, it takes its own time. The water network model alone will take its own time. But when you combine these two, then we are asking for trouble in terms of time. So we have to come up with the ways of solving this. And that is the message this morning. So we came up with a method. This is very, very recent, by the way, maybe published early this year, if not late last year, where we came up with the bridging algorithm. Now, when you do scheduling of batch plans, we always have to contend with the representation of the time dimension. We can either have what we call the discrete time formulation, where the intervals are very continuous over the time horizon, are very equal over the time horizon of interest. And we've come to abandon that now over the years because it's concomitant with a very high number of binary variables. So we are moving into the continuous time representation. But even there are 2 ways of doing it. You've got what we call the unit-specific time representation, meaning that a time point, say, for example, P1, can represent different things for different units. So there P1 is the beginning, which is at a different actual time. And then P1 there is the beginning, which is at a different time. So basically you can see that P1 here and P1, they mean different things in different units. So the time point is specific to a particular unit. But you also have a global event representation like this here, where each time point means the same thing in each and every unit. These are well developed, by the way, these methods. Some of them we developed without realizing exactly what we were doing. And then we've now categorized these two into the unit specific and the global event point. What we tried to do then was to take advantages of both, because they have their advantages. And again, even with these, it depends on the nature of the problem that you are trying to solve. There are problems which lend themselves to the global time representation, and there are problems which lend themselves to the unit-specific time representation. So we took advantage of this. So if you continue, what you did was for the specific unit-specific time grid, we do our scheduling. So this is very, very efficient just for scheduling. We did not look at water, just we do the scheduling there. So we know exactly when a particular unit has to be active, and we know exactly what that unit has to be processing at a given point in time. So that's the essence of the scheduling here. And all of these problems that we looked at are in the max span minimization zone, meaning that we know exactly how many batches we have to produce. What we don't know is what is the minimum time to achieve that. So that is basically what we did there. So this is the scheduling problem. And then after we've done the scheduling, we apply the bridging algorithm. We introduce two new parameters. I'm not going to go into the very detail of this. It's published already, but we introduce new parameters which link this dimension to that dimension. And what that allows us to do is that when we do the water minimization, we no longer have the integer variables because they are fixed from scheduling. So we only have a non-linear problem, which is not really difficult to solve. So it's not a discrete problem. And ultimately, then we do the iteration to get to the solution. I'll give you the results now. Just continue. So basically, this is a hybrid representation of the time domain. You either have one of the two, but to put them together is not something that we had seen in the past. And it does come up with some benefits. It doesn't mean the problem is entirely solved, by the way. So this is the algorithm in its entirety. So we have all the parameters, we have all the constraints. These are our typical scheduling constraints. We have a traditional MILP model, which is based on the unit-specific event. And then we solve that model using our solvers. And there are a number of solvers that can do this. The one that we seem to be, or my students seem to be really attached to at the moment is Baron. But I've come to realize that Baron is not your best solver. If you want a global optimum, maybe, and you can find the solution, maybe Baron is the way to go. But there are solvers which are also powerful in the same platform GAMS that we've been using all the time. So this is a MILP, then you get your optimal schedule, and then this is where you apply your bridging algorithm. And then from there, with your optimal schedule and the bridging algorithm, so you have all your binary variables now as parameters. You have an NLP problem there. This is where you do your water minimization, and that should give you your optimal water network. Continue. The problem itself is based on a superstructure that you can see here. This is the superstructure. So these are the stages that I presented to you earlier. So we can have any number of these stages from that point to that point. And then in between these stages, we've allowed some storage. So some of the water can be stored here. And we do this really as the time buffer. The storage provides that buffer for time, meaning that you can actually override time. You can store some of the material here that can be used later. So we need storage in order to minimize the amount of water. So this is a typical superstructure. So somewhere there, we have an optimal solution. So continue. And then if one looks at this, one of the case studies that we looked at, so we are given all this information. In fact, we've been working with this case study now for a while because it's based on a company here in India. I can't remember the name of the company, but Prof. Raja Gopalan Srinivasan and Prof. Babji Srinivasan would know perhaps which company it is. But we've been working with this case study in particular from an industrial partner here in South Africa, in India. If you did attend Babji's presentation, you would have seen that he also spoke about more or less the same problem. So here you've got 14 stages, and each stage, of course, will have its own units. And these are the types of materials that have to be produced: colors, white, light, medium, and dark. And then we are given all the information as well in terms of the duration in each of the stages in the unit. Okay, continue. And then these are the storage tanks that you have there. So these are the storage tanks. These are the 14 storage tanks that you have. It is by chance, by the way, that we have 14 tanks and 14 stages. Just by chance, you can have any number of stages. And then we have the fresh water that you get here if you do the optimization. So there's a gap between these two, as you can see here, which means that this particular problem was solved. We have the very, very good results, but it was not solved to zero gap between your current solution and your actual solution. So basically, it's still suboptimal, but it's much better than what we had before. And here you've got the sequence in each and every unit. So these are the units that you have there. So in each and every unit, this is the sequence of the colors. This is the dark, the medium, the white, and the light. So continue. And one thing that we saw also was this. We've always known this. I just illustrated it. We know this. So here there's an element of practicality. We might not need to go all the way to that number of tanks. We might decide to stop somewhere there, depending on practicality. The amount of water is still decreasing if you go all the way down there. It's still decreasing, but very, 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 very insignificantly. So somewhere here, you might just have to stop in terms of the number of tanks and also in terms of cost. And then this is the optimal schedule for the entire plant over the time horizon there of about, say, 1,900 minutes. By the way, if I can tell you now, using to do scheduling for a combinatorially expensive problem like this over that time horizon is not very straightforward. That just tells you how behind, or I would say how difficult it is still to solve this problem. If you're looking at about, say, even 24 hours for a combinatorially complex problem, it's still difficult really to find a solution in reasonable time. And we do scheduling really so that we can react to whatever situation in practical terms, which means that the CPU time ought to be in the region of minutes, if not seconds, for it to be practical. And we are nowhere close to that. But at least we can see the solutions. It is progress. It is very much, colleagues, similar to nuclear fusion. I think you had the hype about nuclear fusion. Even yesterday, everyone was still talking about nuclear fusion. It's a very small step, but it's in the right direction. So it is the same thing here. So let's continue. Now, I will talk about, briefly, I will talk to you about the shale gas exploration. And of course, as I say, I mean, you go to the US, I'm working with some guys at Texas A&M, Professor El Halwalji, also one of the leading figures in process systems engineering. They've been working a lot of for quite some time in this project. And the question that I asked was, why still on hydrocarbons when we could be looking further than that? But they say the reality is it's there at the moment, it's on the ground, and we should find ways of doing it in the best way possible. So that is why we are doing this, the scheduling problem for the shale gas exploration. So you can see that it's predicted that even there, we've signed all the treaties, but still, this might increase by 50%, particularly in the US by 2040. And these are the production of natural gas, and these are the prices, as you can see. The reason why this is coming down is because of course, that's the exploration of shale gas. So they said, let's proceed. And they still get a lot of funding from these institutions. Let's continue. And then the challenge, though, which is why we are involved in this work, here I'm looking, shale gas is through hydraulic fracturing. That is how you get your shale gas. That uses a lot of water. There's a lot of wastewater. When we say highly water intensive, talk about fresh water and wastewater. A lot of water is generated there. That is the biggest problem. And of course, there's a lot of flaring where you actually do the extraction of the gas, and there are issues of production costs. So we had to take all of this into account. So it becomes a very interesting mathematical problem in terms of optimization. And then what we're looking at here is a system where we had both dry gas. Dry gas is the gas that you can take directly to customers, and wet gas is the gas that will need some further processing. So we're looking at both these together, right? And then here is the nature of the problem. So we are dealing with water. We have a membrane system here so that we can regenerate our water and reuse it in the process. And of course, there's a gas network then to deal with the distribution of the gases. And then we have to do the well-packed scheduling. And then, of course, that all constitutes what you call hydraulic fracturing. So that is the system, in short, that we are looking at. We have water acquisition that you have to worry about, shale gas production, the usage of that, transportation, as well as the processing of the gas. And these are the parameters that you'd have to be given. So you are given all this information here. In most instances, this is known very well, by the way. So in most instances, this information is available for every well pad. And then we have to determine the amount of water in particular that you have to use. In this case, you also have to look at the distribution of the water. So the distribution of the gas, because we have both dry and wet gas. Again, here we started off with this superstructure. This is the superstructure where you've got the water impoundments. This is where you store your water. Uninterrupted water supply is the water that will always be there all the time. It is counterintuitive, by the way, that what you see there is a river, the representation of a river or a pond. So this is interruptible water supply. It's counterintuitive because we'd expect that from the river is uninterrupted. Actually, you do have droughts that make that inaccessible. Whereas if it's brought in there by the tankers, that can always be organized. Sometimes they have to go a bit further, but they will always be a guaranteed amount of supply there. So this is uninterruptible freshwater supply. This is interruptible. You store it in the impoundments, and then ultimately you've got the well pads there where you process this water. These are the well pads where you get your shale gas, and ultimately your water can be treated. Then this is the regenerator that I spoke about. In particular, in this case, we looked at the membrane distillation as the regenerator. You also have the power plants where the water would end up, and then you've got the customers as one of the recipients of the gas. So in a nutshell, this is how the superstructure would look like. So this is the basis of your mathematical formulation. Continue. And again, these are the constraints which I did not bother putting out in mathematical form. So you have to, these typical scheduling constraints really that you would need in a typical plant. So what we're doing here is taking the work that we've been doing for chemical plants and applying it in a different setting altogether, which is the shale gas exploration. And then these are the assumptions that are made. All of these assumptions, by the way, are very, very practical assumptions. For example, the price of natural gas is independent of time, which is the case because it's regulated in most instances. Let's continue. And then the idea here is to maximize profit, and our profit is defined as the revenue minus the total operating costs. So these are all the costs that we're talking about here, the operating costs. Right, let's continue. So looking at one of the case studies, this again is now a practical and arguably the largest shale play in the US, Marcellus. So almost everyone who's working in this area will give you this case study here. It's a practical case study, actually. Most of the people will be trying to solve this problem because it's a real life problem. So it was studied, these were not the first, by the way. The 2015, it had been studied before, but not using a systematic method, but this was one of the first systematic methods. And I think this is the work of Professor Grossman at Carnegie Mellon University, this case study over here. So here you've got 14 well pads, and then we are looking at a 3-year time horizon, and we looked at through scenarios where we look at the wet gas network as well as the dry gas network. And this is the problem description. So you've got two impoundments here. Water is distributed into two impoundments. So you've got that two regions. That's the region in terms of the geographic area. In that region there, you've got 6 well pads, and in this region here, you've got 8 well pads, as you can see there. So these are the rivers or ponds where you get the water from, and this is the tank. So this is the additional information that we have. Standard information, really. And then this is the ultimate schedule that you get for the wet gas scenario and the dry gas scenario. If you continue, I'm just looking at my time. We also did some thorough cost analysis in this, in terms of both the scenarios, looking at the wet gas scenario and the dry gas scenario. And you will see the reason why we look at different scenarios is because the other one has to be more expensive in the sense that you have to treat the water. So you have to treat the gas before you supply it to customer. And then if you continue, so this is the flow sheet now, the optimum flow sheet for the wet gas scenario, where you generate, this is the processing plant. The processing plant here is really for the gas that you produced from there. So you generate your gas, and then you process that gas, and ultimately it ends up in power generation. So that's the power plant there. So it has to be processed before it gets into the power plant, and then ultimately the power is distributed accordingly. So this is the wet gas scenario, and then continue. The next one is the dry gas scenario. So this one would be a bit cheaper because here you don't need to have any treatment facility for the gas. The gas is dry already. And then in closing, I just want to say a few things about this unit commitment problem. Really what this pertains to, and I'll be closing now, is making sure that we have secure supply of energy. The reason why South Africa does not have electricity at the rate at which it's supposed to is a very strange one. We understand why Europe is having issues with energy, but the South African problem is a very, very interesting one. We've got 48 gigawatt of installed capacity. We use, under normal circumstances, nothing more than 30 gigawatts. So we've got more installed capacity than what we use, but we still don't have electricity. It just defeats all logic, does not make sense. And one of the reasons for that is because we've got aging infrastructure. So what is called the EAF, the electricity availability factor, is very, 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 very low in each of the plants, sitting below 40%. So as soon as you go below 50%, even in your typical chemical engineering plant, if you go below 50% in terms of availability, that plant is as good as not there. So that is basically what we are having. It's because of the issue of the aging infrastructure. So for those who tend to visit me at times, they must brace themselves for that. Iqbal, there might be load shedding next time you come there. So let's continue. And then this is the typical information that is given. But the point that I want to raise, this is general stuff in terms of scheduling. We know this, so we're applying again what we know. We're working with the government entity they're known as Eskom, which is the sole supplier of electricity, to try and solve this problem. This is your typical scheduling problem. But continue, and the problem itself has been solved, by the way, in different ways in the past. So there are two types of the unit commitment problem. The profit-based unit commitment problem, which will not apply in South Africa because we're a regulated country in terms of electricity, and we've got main supplier, which belongs to the government. So this applies where we have a deregulated system, so everyone wants to make profits. It might happen in future when we have our independent power producers, but for now, it's not the case there. And then we've got the security constraint unit program, where we've got a vertical integration. So this is the case with South Africa. And the idea there is to try and maximize the spinning reserve. So the spinning reserve is your extra generation capacity from some of your committed units. So the units are already working. How do you make sure that you maximize that spare capacity so that whenever there's an emergency, you can ramp up as soon as possible? So that's the idea behind this. So let's continue. These are the methods that have been applied in the past. Heuristics, we also know these methods, and this is the one that we were applying in this case, so deterministic approaches. Let's continue. And all the methods that have been used in the past tend to use this because the problem is easier to solve using a discrete time formulation rather than a continuous time formulation. So there you have to come up with a new formulation really altogether to be able to do what this formulation can do. The beauty of this is that you have fewer binary variables. That's the only reason. Okay, so let's continue. Let's continue. This one is animated. Continue. Yeah, so So basically you'd solve your model here initially, and then once you've solved your model, this is a continuous time model, and this is the unit specific event point modeling. We do the same parameterization that we did for the textile industry. So we fix some of the variables here after scheduling, and then we map the difference between what you would have received via discrete time formulation and the continuous time formulation in order to get the final model that uses the demands. And we also include the uncertainties, by the way, in the demand. If you continue. Yeah, so basically in the cost function, we are interested, this is the cost of fuel, and this is the cost of startup of the units. So we've got a hot startup and the cold startup. A hot startup is really saying the unit is already working, and then we ramp it up to the desired capacity. The cold startup is not working. And when I say units, I'm talking about the turbines. So these are the generators that we're talking about here. So if you look at the results, so we looked at, yeah, continue, let's just continue. Continue. The point I wanted to illustrate here is we looked at a problem with 5 units. The 5 units are the 5 generators, your 5 turbines, 10 turbines, and 20 turbines. And we found that different formulations perform differently according to the number of the turbines that you have. And so this is a problem that is still being solved, by the way, because these were fixed a priori. These are not the outcomes of the optimization exercise. So we fixed this beforehand, and then we solve the problem. We can see that it does depend on the number of the units or the generation units. And this is a very good observation, by the way. And then this is the scheduling. The reason why we get a good performance for 10 units is because you can see here, you don't have too many startup and shutdown. You don't have too much of that, which is very good. But the more startup and shutdown you have, the more costly it is to run the facility. And of course, in terms of availability, it affects it. So I'll be closing now. Yeah, so this is the parity function that we use, which is the measure of system insecurity. So the idea, you want to reduce this, you want this value here to be as small as possible, ideally. And for this particular problem of ours, just continue. For our problem, that value was sitting there, which means that you've got more availability than you would have. This is the discrete time formulation there. And that answer or that result has been obtained by a few authors. Let's continue. And then what we are trying to do now is to look at much longer time horizon, looking at cyclic methods. And of course, one of the ways of doing it is to look at the wraparound scheduling. So this is the type of work that we're trying to do now, to look at much longer time horizons instead of the short time horizon. Let's continue. And then if you look at some of the results that we've gotten, this is the last slide, colleagues. Continue. No, just back. Yeah. So if you look at, just back a bit. If you look at the results that we've received here, so for non-periodic long-term scheduling, in other words, you solve the problem without looking at cyclic scheduling, which is very, very difficult. It takes just a bit longer. And then the result, of course, it's a bit low in terms of the overall cost. So you spend less, because the idea is to minimize the operating cost here. And in periodic scheduling, so there is some element, some degree of freedom that you lose by going the periodic route. And there you can see that you compromise on the overall cost. And of course, it also takes a very long time. I just want to thank everyone that is funding us in this work. My university, that is investing heavily in the work that we do. We are a research-intensive university, so there are not many universities that put so much money in research. And then, of course, our National Research Foundation. Thank you very much, colleagues.
Yeah, thank you, Professor Majusi, for this exciting talk, not only from PSC perspective, but also to make us aware of how our day-to-day things affect carbon and water footprint, which is important for countries like India and South Africa. We have time for a couple of questions from the audience.
So, thank you for presentations from François Maréchal from EPFL. I have a question concerning the decomposition method that you are using, because you go from scheduling to then nonlinear optimization. You do not introduce a feedback loop, so that you can then perhaps reformulate the scheduling problem as a function of the results of the nonlinear parts.
Yeah, that's a very good point. If it was a decomposition method, we would do that, because you'd have to, your Danzig wolf kind of thinking. If you decompose, you'd have to then have that feedback loop all the time. It's not a decomposition problem. So we were solving the same problem, but you discretize it into your scheduling first and then your water minimization. So it's a two-stage problem. We don't go back. So we are solving different problems. We don't decompose, solve different levels, and then do the comparison between the different stages like you would do, for example, for your GPT. It's not like that. And maybe you just should emphasize the point. So in scheduling, we forget about the water recycle and reuse. We still have the water constraints, but we don't look at options for recycle and reuse. So we get the best schedule. And that is what people will want in practical terms. That takes priority. Your schedule takes priority, because once they've determined that it's X amount of garments that have to be produced of a certain color, that has to be obeyed. Once we fix that, then we say, how do we achieve this using the least amount of water? All right. It's a problem that, in my opinion, could have been solved by anybody. So you could actually take the same model and solve for water minimization. The only problem for that is that it takes too long. So to minimize the amount of time, we fix the variables, meaning that we now know which units are active at any given point in time. What we do not know are the recycle and reuse opportunities. So we only explore that in the second stage. So it's not really a decomposition method. I think Raj wants to say something. Oh, okay.
But then I have a question, because it's possible that the scheduling is going to penalize your water usage.
No doubt about it. So you have to then make a decision. You're 100% right. Your scheduling is likely going to penalize your water usage, but also if you place emphasis on water, your water will penalize your scheduling. But practically speaking, it's better to penalize your water, because that is what industries would go for. The planning is influenced by a number of other issues. For example, the demand on the other side beyond the battery limits of the facility. So the first premium is getting the schedule right, but you get that schedule using the minimum amount of oil. So the water minimization then becomes your secondary objective, if I can call it that.
Okay, thank you.
Thank you, Toko, for a very interesting presentation. I had just one kind of philosophical question that I know it always has been in my back of my mind. So it looks like scheduling and optimization in general is very much a niche area where you really have to be in it, have put in a number of years before you know how to get it going. What do you think it's going to take for us to go from that to something like Aspen, where a person with maybe a couple of days or maybe a week of experience can at least get some value out of it, maybe not the global optima, but something that optimization and scheduling particular can become widely useful.
It's a very, very good point. And we've been at this now for a very long time. This problem, comes, well, in the 70s, if someone was, well, they were using very, very weak computers or poor computers at the time. We now have significant computational power, but we still have not really made some serious breakthroughs in terms of CPU time. My philosophy or my thinking is that, and this is really against my conscience, because I'm married to the deterministic methods and I've been working on this for a long time. I still do. But I think that that's no longer the way to go if we want to solve problems very quickly. If we really want to solve problems very quickly, we must start looking at other methods like your evolutionary algorithms, for example. One is talking about genetic algorithms or any other stochastic method, or even the new ones now that are coming via AI. But somewhere there you still have this deterministic engine. So you have a hybrid kind of an arrangement where maybe your AI engine can give you a starting point for your deterministic model. So that might make things easier. So when you start solving because the starting point for deterministic models is very important. Where you start is very important. So if you can start closer to what we call a global optimum, that might perhaps lead to quicker solutions. That is what I think is going to be the case. But deterministic route alone is going to take a very long time to bring us to where we want to be. And maybe it's not the only way to take.
So one quick question. So have you seen in industries where the treatment happens at local level instead of mixing water from different stages at the end? Is there a benefit in treating the water at the local level because the concentration will be known? And is there somebody doing it in industries?
It's usually not the case. It's usually not the case, but there are many benefits in that. I think it's a historical thing. You would know that other than saving water, if you treat locally, you also recover some of the material.
Yes.
As soon as you start mixing, you lose that opportunity. So as to why people go for that, loss, it's very, very interesting. Because historically, you'd find that we didn't have issues with water, but in most countries, and even the constraints or in terms of the legal limits or as to what you can dispose with have been very relaxed over time. Now that water is becoming an issue, people are starting to think about it very, very seriously. I can share with you now, I might have presented it somewhere. We did some work with Johnson & Johnson in South Africa. Johnson & Johnson, as we know, is a multinational US company, but they've got a pharmaceutical facility in South Africa. And they make this Johnson & Johnson baby lotion, that pinkish one. I think you have it here as well. When we visited the facility, they were losing in excess of about 10 million rand in terms of product per year. Because you put your lotion in the vessel, you do the mixing, you empty the vessel because of the viscosity of the lotion, some of it remains on the walls. You then spray the walls and you do away with everything that comes from there. And there's still product there that's not recovered. If you could recycle that water, because it's an aqueous space mixture, you could still use it in the next batch and recover that amount of material that you lose. So when we did the work, simple optimization exercise, we could see what opportunities there were in terms of recycle and reuse, and they adopted that. But there are not many companies that do something like that. The recycle and reuse locally, that is happening, I've seen, but treating locally, that's a different matter altogether. I think it's because of investment as well. But things might change going forward because of the environmental issues, and the costs are coming down in terms of our understanding of treatment plants.
Thank you. Thank you.
We'll thank the speakers.